Hello everyone. My name is Paulo. I'm the founder of OAI, and I'm here today sharing the webinar that has different components, starting by sharing my screen. Let's say the most important thing is at the end, where you are going to run a live demo of ISAC technology using OpenAirInterface. So Camille, just confirm that you can see my screen.
Yes, I can see it.
Okay, thank you. And I'm happy to see more than 100 people join today. Actually, ISAC is a key topic for 6G research, and OpenInterface is a great tool for doing research on this topic. So the plan for today, first of all, the speakers. So from OAI Smart, it's myself. We have also Tiago and Luis. And we have Ibrahim from Interdigital that I hope is joining. The idea is that Ibrahim can bring us an industry view of ISAC standardization perspectives. Okay, so this webinar is also supported by the European Horizon Europe Converge project. I'd like to acknowledge Converge project that has been working for the last 3 years on building a research infrastructure that combines radio, vision, and sensing technologies to enable new research areas based on the motto view to communicate and communicate to view. So if you are interested or understand better the Converge research infrastructure that is available through third parties, just Google Converge or find this web page where you get more information about the Converge chamber that allows researchers to test ideas around joint communication and sensing and ISAC. OAI Smart and Interdigital are both members and Eurecom of this joint effort funded by the European Commission. Okay, so the idea for today in terms of agenda is start giving motivation and use cases applications of ISAC. Then we'll go through industry perspective on the standardization in ISAC. So what is the plan for 3GPP, for ETSI and ITU in terms of roadmap for ISAC. Then we go more technical on the 5G reference signals that can be used for ISAC experimentation using OpenInterface. And then we have a live demo from OAI Smart headquarters, where we are going to show live a system that counts people in a corridor using 5G signals. And then we will have Luis explaining how to extract the 5G channel estimate that is used for ISAC experimentation from the OAI stack. So this final part is going to be more hands-on, having Luis explaining how to extract the channel estimations from the OAI code that I think most of you are interested. And of course, we will have time for questions and answers, and we can also continue the discussion offline because I will leave here our contacts. The slides will be available. The code will be available in the OAI repository for experimental replication. You can always find us through the oaibox.com website or even directly to my email. Okay, starting by the motivation use cases and applications. I'm sure that you are aware about what integrated sensing and communication is emerging as a key capability for 6G, enabling the joint use of radio spectrum and network infrastructure for both environmental sensing and data transmission. So the idea is that ISAC can detect passive objects not connected to the network, like radar technology does today. With ISAC, mobile network operators can reuse their cellular infrastructure as a sensing network, enabling detection without the privacy concerns associated with cameras and reaching areas where video cameras cannot operate. Mobile network operators are very interested in this technology because they see a new monetization opportunity, which is critical in the road towards 6G. So if you look to the 3GPP Technical Report 22.837, you will find 32 use cases for ISAC. So just listing some of, let's say, most important: intruder detection, so detecting human movement. Actually, today in our webinar, we are going to demonstrate an application of counting people in a corridor using OAI. Object detection and tracking, detection of vehicles, or UAV sensing, drone trajectory tracking, smart infrastructure monitoring, industrial sensing, like monitor the movement of robots, environmental sensing, or automotive and road safety are some of the verticals that can benefit from ISAC technology. So how ISAC works? Let's go to the physics. So by estimating the radio channel impulse response, or the channel frequency response, that is the Fourier transform of the channel impulse response, an ISAC node detects weak changes in the radio propagation channel, which correspond to the human or object's presence and trajectory. So now if you take advantage of AI, ML models, these models can learn these complex patterns for a reliable detection. The point is that there is no need of dedicated radio spectrum, so mobile network operators can reuse the spectrum they already have for communication, and also can reuse part of the infrastructure they already have. So it's a quite attractive use case for 6G. So in this picture, you can see a transmitter and the receiver. You have a direct line of sight, and then you have two paths, path 2 and path 3, that are reflections on these walls. So if the transmitter transmits an original signal, like a carrier, this signal gets at the receiver delayed, attenuated, and you have multiple replicas of the signal because of the reflections. So this can be seen on the channel impulse response, where you have the line of sight, path 2 and path 3. So now we have a drone here. So the drone will appear as an extra and additional multipath component. And if the drone moves, the multipath component changes position. And also the amplitude and phase of the frequency response will change with the movement. So if you have the capability to analyze these movements of these changes on the channel response, we should be able to detect the presence of this drone and the movement, because this is also related with the Doppler shift, if you want to estimate the speed and the distance that the drone is from the receiver. So leveraging the rich multipath channel state information, you should be able to detect the presence of people and obstacles or objects. So some time ago, we released this video to motivate people that is using OAI to explore ISAC. We got a lot of feedback and views. So I have here some print screen. So the idea is to showcase how to see through walls using ISAC and OpenAirInterface. We have a user equipment, an iPhone, in this room. And then when a person comes, the reflection on the person is changing the multipath radio environment. And then if you now approach to this wall and go to the next room that we call the surveillance room, we have USRP connect to a computer platform that runs the core network and the G-Node B using OAI. And then using OAI, we can extract the uplink channel estimate over 100 megahertz. And this gives you information that you can explore to try to detect the presence of a person beyond this wall. In fact, as the person is moving, the radio channel shape is changing. For instance, when he's passing in front of the UE, it has a particular signature. So this is very important to highlight, because ISAC can see where video cameras cannot see, because radio waves, because of the lower frequencies, can go through walls. And this is a strong point and a strong advantage for ISAC applications. So if you want to follow us on YouTube, you should be able to see a lot of demo videos that showcases OpenAirInterface applications, not just for ISAC, but for FR2 or AI run or network slicing or Open Run, configurable intelligent services, Industry 4.0 applications, FR3, and others. So every month we publish new YouTube videos with use concrete examples of how leverage OpenAirInterface for 5G, 6G research. So we have very happy if you can follow us and subscribe our YouTube channel. Okay, now we have a plan to move to the interdigital view on ISAC. Not sure if Ibrahim has joined us.
Yes, hello, Paulo.
Great,
Yeah,
Ibrahim.
here.
So now Ibrahim will give us an industry perspective on ISAC and updates on ITU, 3GPP, and ETSI. So I'll stop sharing my screen, and then Ibrahim, please, the floor is yours.
Yeah, thank you very much, Paulo. Just give me one moment. All right, can you see my screen?
Yes.
In full screen, right?
Yes. Yes.
Yeah.
All right, perfect. Yeah, thank you, Paulo, for the invitation. Happy to be here and to see this this live demo on sensing. What I'm going to present here is, the industry perspective on ISAC, and I'll provide updates from ITU, 3GPP, and ETSI. You know, sensing is not yet specified, so it would be quite interesting to see how you use this uplink in order to do the sensing. So starting with the timelines, can you see the slide?
Yes.
All right, perfect. So in 2021, following the completion of what we call IMT 2020, which was essentially 5G, ITUR launched the work for IMT 2030, which is essentially what we call 6G. And they followed the conventional process, so we'll have 4 phases. Phase 1 will have the framework, phase 2 will have the technical performance requirements and evaluation criteria. Then we have the evaluation, and eventually we'll have the IMT 2030 specifications and approval. As of today, phase 1 was finalized, laying down the IMT 2030 framework, and currently we are towards the end of the IMT 2030 technical performance requirements. I will talk about this one in a minute. There is a milestone workshop happening early next year, which will basically kick off the launch of the 3rd phase in ITU. That's mainly in ITU. So, and in 3GPP, the development of ISAC in 3GPP began during what we call the 5G Advanced. So this is basically release 18 and onwards. Here we have 3 main components that I will be discussing. So we have the 5G track and we have the 6G track. In the 5G track, we have release 19, ISAC in the release 19, and then ISAC in the release 20. And then for 6G, we have the new study on 6G for this one. All right, so starting with the IMT 23 vision for ISAC. So, you know, IMT 2030 published the recommendation. In this document here, I'm 2160, and they identified 6 usage scenarios. So we have 3 scenarios, if you can see the screen here, this figure. So the green ones are extensions from 5G, you know them like EMBB, URLC, so on and so forth. And you have the new ones, which is ISAC, Integrated Sensing and Communication, AI and Communication, and Ubiquitous Connectivity. And this framework basically introduced new sensing capabilities by focusing on sensing, such as range estimation, velocity estimation, angle estimation, and also some weighing measurements, such as the accuracy, the resolution, the detection rate, so on and so forth. And recently, we have what we call the unified requirements. This was published by the working party 5D in ITU. They outlined 20 performance requirements. You can see like it's quite small, I know, but if you look at them, the bold ones are the new ones for 6G, and number 17 is on sensing related requirements. Okay, so that's for ITU, and now going to release 19 on the channel modeling, which was the main focus on it, was on the channel modeling. So here 3GPP at the start of studying this 5G, 3GPP recognized that the existing channel model specified for communication needs extension to enable proper evaluation of ISAC performance. That's why they had a study on channel modeling for integrated sensing and communication. I'm pretty sure part of what you did, Paulo, you're looking at some uplink signals, doing some measurements. So when you want to, the first step would be, like from the 3GPP perspective, would be the channel modeling. So now this is already available in this document. You can just type it and you can find this one. So the sensing channel model is already defined in this document. It covers these scenarios like UAV, human, vehicle, AGV, and hazard. Also, there's like 6 modes. Bistatic and monostatic. In your case, you have the uplink, which is the UETRP bistatic. So this is one of the modes. So briefly, what happened here is they introduced the new sensing channel, which basically characterizes the target in an environment, and then they have the communication channel model, and they combine them together. That's why we'll have the ISAC channel would be the channel of the target plus the background. There are a few new components in this channel, which is the RCS, the radio cross-section model. We have the segmentation of the target. We have the line of sight, non-line of sight coupling, type 1, type 2 environmental objects, or those are objects in the environment that are not the targets, basically. There are some other aspects such as the polarization and microdoppler. So these were all studied in the channel modeling in the study for the channel modeling in the release 19. So there was now a follow-on study on integrated sensing and communication in the release 20, which is still 5G here. And the main focus here was on monostatic sensing for UAV detection. So here we're still talking about the TRP on its own, no TRP, inter-TRP coordination, no UE involvement. So if I look at the demo that you're going to present, it's quite beyond what we have here. Because now what's being studied is basically monostatic TRP, the genome B transmits and receives at the same time, and that's mainly it. They are reusing the current NR waveforms, which are based on OFDM. Downlink you have OFDM, and then in the CP, and then the downlink and the uplink you have OFDM or the FTS OFDM. Right. So for the work for RAN 1 finished, which was on the evaluation of the performance of the genome B in monostatic sensing. But now currently ongoing, we have the work for study for NR3 to look at the procedures, the signaling between the RAN and the core network, as well as the architecture. So this is supposed to conclude in June 2026 in terms of timeline. So for 6G, so you can see here I didn't talk about any technology because basically this will all be here. There's this RAN plenary 6G study on scenarios and requirements. If you remember in ITU, I mentioned something on the requirements. So this is, fed into this one here. So there are 2 main sections defined in this document, which is section 5.117, the sensing related requirements, and the requirements of sensing services. Here you'll see that the main components are detection and tracking, which is what you have in this demo, detection of passive objects and other types, as well as the communication assistance. We are still at the early stages, so this will kick off this year, the study for 6G or ISAC. There is one study on 6G radio This is underway, and it will be completed by the first quarter of 2027. They have 9 objectives, and one of them is sensing. And in this one, we are expecting to see, companies providing their input on the what type of waveform, what's the reference signals, what's the measurement feedback, what are the procedures, upper layers, lower layers, so on and so forth. And the 6G, the baseline will first handle as I mentioned, the waveform, the modulation, the very basic things for sensing. That's for release 20. And by the way, there is a meeting happening next month, RAN 1 meeting. And in this one, there will be 3 agenda items related to sensing. One of them is on waveform, and the other one is on the evaluation of sensing. And the third one is on the integration between sensing and communication. So we cannot really say what would be the company's views yet, because this will be in the next meeting. Okay. So that was for 3GPP. We have something running in parallel, which is ISAC NHC. So there is an ISG, which is Industry Specification Group, NHC. These are typically pre-standardization groups where companies and research institutes gather together in order to provide pave the way for future standardization. So initially, this ISG launched in November 2023. The first release was finalized, and they had 5 working items. You can see they run similarly to 3GPP. They look at the use cases and deployment scenarios, the channel modeling, the architecture, the security, privacy, and sustainability, and the computing part. So these GRs are all finalized, and now we are in the release 2. This started in November last year, and we have a new work items. One of the things here, when you look at the channel modeling, for example, in channel modeling, they have some new components like the segmentation-based RCS. They looked at the micro Doppler in depth. They look at the what they call the micro deformation and the rain attenuation. This was included in this work item. We didn't see it in the 3GPP part. So this ETSI ISG group, they have more than 100 members and an associate organization, in addition to 1 counselor from the European Commission. That's in general from the standard activities point of view. I just wanted to put this one here to discuss, maybe to shed the light quickly on the type of the components that would be taken into consideration in the 6G study on sensing. Always when you talk about a new study or a new technology like integrated sensing and communication, you first need to look at the channel. So this has been already defined in the document. You have the target model, the reflection, the clutter, so on and so forth. What will be studied typically is the waveforms. Currently, we have OFDM based, but in the radar literature, we have so many types of waveforms that are considered for radar systems, such as the FMCW, shared-based signals, the pulse signals, different types of waveforms that are being considered. Also, we need to look at the numerology. Are we going to use the same, subcarrier spacing, FFTs, and those kind of things? Also, we have the reference signals. So we can rely in the uplink and in the downlink on the existing reference signals, but the more reference signals needs to be also considered for sensing. Same for measurements. What kind of measurements we require for sensing? Because in sensing, it's different from communication. You need here to look at the range estimation, the velocity estimation, and these sort of things. So this should be studied. And eventually we have the reporting and the processes, the RAN 1, RAN 2, RAN 3, RAN 4 processes, what's required. So that's from my side. Thank you. Hopefully I didn't take much time.
Thank you, Ibrahim, for this interesting overview of the standardization activities in ISAC. I will ask you to stay until the end of the session if there is any question from the audience. Then I will move again to my presentation and we'll continue with the program for today. Okay, so Ibrahim just give us an industry perspective on ISAC, and now we'd like to go more, let's say, technical on what is possible to do today with the waveforms that we have in 5G. So the idea is that we don't need to wait for full 6G standardization that is going to be maybe finalized by 2030 to start using ISAC. So many applications can already leverage existing 5G infrastructure and reference signals and reusing the available radio spectrum. And for this, OpenAirInterface, through its open source GNodeB and UE, provides access to the 5G reference signals that can already be used for ISAC experimentation using today's 5G waveform. So the focus of today's webinar is more on reusing the existing 5G waveforms rather than design new waveforms to improve sensing. So Ibrahim just mentioned the importance of the channel modeling. Here, a very simple background on radar technology. So the monostatic radar, the transmitter and the receiver are located in the same place. So the transmitter transmits signal pulse that gets reflected in this object, and then the receiver will receive very weak signal, probably that gets from the reflection. So if you look into the radar equation for the monostatic radar, the receive power is the transmit power times the gain of the transmitter times the gain of the receiver. Here you have the radar cross section, wavelength, so this is a constant, but the point here for the monostatic radar is that the distance appears to the fourth power. So the signal that we get here is very weak compared with the signal in the communication because in terms of communication, when you have line of sight, you have the square value of D. Here you have the D to the fourth power, which means that it's quite challenging to receive a very weak signal that gets reflected by the object. Of course, this also depends on the radar cross-section, that depends on the object, and this is why it's important to have these ISAC channel modelings that allows the simulation of the ISAC operation. For the distance estimate, in this case of monostatic radar, so to estimate the distance, first you need to have an estimation of the round trip time, the time that the signal takes to gets reflected and come back to the receiver. So over 2 times the speed of light, you have an estimation of the distance that the object is from the radar. The time resolution is related with the bandwidth, is 1 over the bandwidth of the pulse. So the range resolution is C times the delta tau over 2. So replacing delta tau here, it comes that the range resolution is the speed of light over 2 times the bandwidth. So why this is important? Because this gives you the physics limits of range resolution. That is the minimum separation between 2 targets that allows the radar to resolve them as distinct objects. So regardless the machine learning or AI advanced algorithms that you may develop, we have the physics that limits the range resolution. So looking for typical 5G bandwidths, 20 megahertz, you get 7.5 meters of resolution, 100 megahertz, 1.5 meters. In FR2 with 400 megahertz, you may go down to 37.5 centimeters. And then imagine in FR3, if you have 1 gigahertz band available, you can go down to 15 centimeters. Actually, FR3 is a quite interesting band for ISAC because today a lot of radar systems already operate in FR3. So it will be important later for us to compute the range resolution. So Now we are going to explore the existing 5G reference signals to implement ISAC use cases. So we have, let's say, two approaches. The first, ISAC using 5G downlink reference signals. So the sensing is done in the UV side or in the ISAC node. So for this, you can reuse the SSB signals or the SSI-RES signals. Another approach is to use the uplink reference signals. The sensing then is done on the G-node B side, and we can explore the uplink SRES signals. So different approaches have different advantages and disadvantages. Today, the demo we are going to do is on the second approach, but let's go more deep on the reference signals that can be reused in 5G for ISAC applications. So SSBs in the downlink. So this is the synchronization signal block, is a broadcast signal transmitted periodically by the G-node B and is received by all UEs in the cell without any priori connection. The SSB includes the primary synchronization signal, the secondary
Sorry,
synchronization
Paulo,
signal.
are you sharing your screen?
Yes.
I can't see the screen. I don't know how is that for
No.
others.
I can see it.
We can see it.
We can see it. We can see it.
Okay.
See it.
So here you can see in this picture the SSB structure that is composed by 4 OFDM symbols with this structure. So if you use SSBs in the downlink, ISAC doesn't require prior access to networks configuration. This is a topic that Ibrahim mentioned in the presentation. So there is no need for cooperation with the G-node B. You can use explore ISAC with existing signals. You don't need to tell the operator or the G-node B because there is no need of configurations that are required for explore SSBs. Sensing is done on the UE, on the ISAC node. The limitation is mainly related with the range resolution because the bandwidth of the SSB signals is 240 subcarriers times the space carrier separation. There's this 30 kilohertz, which means 7.2 megahertz. So the range resolution is not great, it's just around 20 meters. It can be useful for some applications, but it's again the physics limits that comes from the limit bandwidth of these signals. In terms of time domain, this is the time and frequency, the domain position is a periodic signal that is repeated every 20 milliseconds, but is also configurable. And today OAI allows you to test these different configurations. So another approach for using downlink signals is to explore the CSI-RES. These channel state information reference signals enables downlink channel estimation by the UE. So by default is a signal designed for estimate the downlink channel. The combination of wide bandwidth, beamforming, and configurable transmission patterns allows CSI-based sensing to achieve high spatial and temporal resolution. Here, the point is that ISAC requires prior access to the network's configuration. So you need cooperation with the G-node B. You need to know the structure of the CSI grid to explore this information, so this data. In terms of bandwidth, the maximum bandwidth is 100 megahertz, which is good for 5G FR1. Range resolution goes down to 1.5 meters. If you want to understand more about the CSI structure, these are the 3GPP technical specifications. Actually, it's quite complex how the structure of CSI is designed in 3GPP. You need to have access to these tables with a frequency and time domain structure. I will leave you here a very interesting YouTube video with a detailed explanation on how to generate these structures, and OAI has already implemented and are ready to be used by the OAI community, the SSI, if you want to explore downlink reference signals with 100 megahertz bandwidth. Okay, what kind of applications are now discussed and useful if you want to explore downlink SSBs or CSIs? The idea of passive radar is something that is becoming more and more relevant, especially for defense applications. So passive radar reuse existing RF signals from external illuminators, in this case a 5G base station, instead of transmitting its own waveform. This enables target detection in contested RF environments without emitting additional signals. So it's a silent radar. Because one of the applications is also to detect these silent drones or dark drones that are drones that we cannot detect because they don't transmit any control or telemetry radio signals. So this kind of drones we can detect using radars. And if you want to be silent as a radar, you can reuse the existing radio waves that are transmitted by base stations like 5G base stations. And for this, you can explore the SSBs and the CSI signals. This is an example of a bistatic passive radar. So as a base station, you can transmit 10 watts or even more. And then if there is a drone, that is a silent drone, estimating the radio channel at the ISAC node, it will be possible to detect weak changes in the radio channel, which correspond to the drone's presence and trajectory. Of course, if you have here the possibility to explore beam scanning, it will improve detection and performance. So how we can explore OpenAirInterface to test these ideas? Okay, I think this is the main topic of today. So the good news is that OAI has the full stack implemented. So what you need is a computer platform running the GNOP in OAI, connect to a commercial radio unit, split 7.2, or you can use a software-defined radio. And this will be transmitting the SSB signals and the CSI by default, because these are reference signals that are used for data communication. So these signals always exist. And then what you need on the UE side, you need to run the OAI UE, and OpenAirInterface is the only open source project that gives you an OAI, an implementation open source of the UE stack, and you need to have access to the downlink channel estimation using the OAI UE in order to detect the changes on the downlink radio channel when the object appears or is moving. So again, if you want to explore downlink signals, you need to have the OAI UE that gives access to these downlink signals. So you can build a test bed in your lab, in your campus, to detect obstacle objects, sorry. So now moving to another approach, using the uplink signals, uplink reference signals. So here we can explore the sounding reference signal, SRS, that is a signal transmitted by the UE and is used by the GNOP to estimate the uplink radio channel. This ISAC technique requires prior access to the network's SRS configurations. So again, here we need some cooperation, or you need to know this grid with the allocation of the SRS symbols in order to estimate the uplink radio channel that you can use for ISAC detection. So here the ISAC illuminator is the UE, so you can explore commercial user equipments, iPhones, Quectel modems as a source of illumination for the ISAC system. Sensing is done on the GNOP. Different UEs have different SRS, which is good because you can play with collaborative sensing. You can have different channels, different perspectives that together it will increase the accuracy of the sensing system. The maximum bandwidth is 100 megahertz, so the range resolution is 1.5 meters. Here is the SRS grid. A typical SRS configuration in OAI is n symbol equal to 1. In terms of frequency domain, the KTC is 2, but again, this is configurable. And OAI allows you to change the configuration of the grid, which I think is a very interesting research topic. What are the density, or what are the impact of SRS density on the quality of the estimation, the position and accuracy? You can, in OAI today, change this configuration and see the impact on the ISAC performance. So if I want to use OpenAirInterface to explore SRS signals, what I need? So I need an user equipment, could be a mobile phone or a Quectel modem, commercial mobile phone that works as a ISAC illuminator. And then we need to have a G-Node B that runs the full G-Node B stack, a radio unit or a software-defined radio. And if you want to explore AI, machine learning at the edge on the G-Node B, it will be useful to have a GPU for training the models that will help you to detect the presence of the object that is moving in the scenario. Actually, today, demonstration is not to detect drones, it's to detect people, but this is the principle that you are going to demonstrate today. So what are the role of AI machine learning for ISAC? If you look to the AI Run Alliance work, they have identified these 3 main use cases for AI Run. So AI and Run, AI on Run, and AI for Run. In AI on Run, the idea is to use AI applications that are enabled by the radio access network. And ISAC surveillance is one of the core use cases of AI on Run. So the GPUs running on the G-Node B can be reused apart from running the 5G stack, for instance, to improve detection at the edge. So this is one of the key aspects of AI on the run. And AI ML can help you to improve the accuracy of the ISAC detection. But for this, you need to train a model. So in this example, we have a user equipment transmitting the SRS signals, acting as an ISAC illuminator. You have here a person that is moving in this grid, and then you have the radio unit, and then you have the OAI stack here running in one OAI box. So if we change the position of this person, the radio channel estimation in the blink will change. If you have a video camera system to record the position of a person, and then if you train the model with this ground truth, using, for instance, supervised learning, you can remove the cameras and using now the live uplink channel estimation with the AI model, you should be able to detect the presence of a person with a specific confidence level. So the cameras are useful for training the model, and then you remove the cameras, and then you can estimate the presence of obstacles and so on. The challenge is always generalization of the model. So a lot of research needs to be done yet here. In terms of architecture, you can use the Open Run architecture and running the AI model as an XApp. Okay, now why OpenAirInterface is so important for ISAC research? Because commercial G-Node Bs and UEs don't expose the required low-level radio channel parameters required for ISAC operation. OpenAirInterface, through its unique open-source G-Node B and UE, provides full access to the 5G reference signals required for ISAC over-the-air experimentation. The machine learning model's accuracy in ISAC depends heavily on data sets, quantity, quality, and diversity. So you need to have a lot of data to train the model. So you need to have an over-the-air experimentation facility. And for this, OAI is well positioned to help you in this research effort. Open source testbeds and open data sets are essential for ISAC research, where achieving robust models and model generalization remains a key challenge. But not just in case you want to reuse 5G waveforms. As Ibrahim mentioned, so there is now an effort in 3GPP to look at the new 6G waveforms that combine sensing and communication. And here OAI is also a good foundation for this effort, because if you change the file layer, you can keep layer 2, layer 3 from 5G, and then you can test end-to-end ISAC with new 6G waveform. So the file layer is also open source and available for fine-tuning, for inclusion of radar signals, for removing some TV slots and using these TV slots for sensing. So a lot of techniques can be exploited using OAI today. OAI enables the exploration of the trade-offs between communication requirements, throughput latency, and sensing performance, localization accuracy, and detection probability at the G-Node B and the UE. So there is a trade-off between the performance of the data and the performance of the sensing. So this requires a lot of research and experimentation where test beds are needed. Okay, so now we are going to have a live demo from OBSmart, but before giving the floor to Tiago, I'm going just to describe a bit the scenario that we have today. So we have an indoor environment with a small cell based on OpenAirInterface with a commercial radio unit, and this radio unit is connected to an iPhone 17. So by the way, a lot of people in the community is asking about supporting iPhone 17. So it's already supported in OAI, and today you are going to demonstrate this. So we have a data link, a 5G communication link. But at the same time, you have here a Quectel modem that acts as ISAC illuminator. So this modem is always transmitting the SRS signals in the uplink, and we would like to count the number of people that is crossing this corridor or that is in this corridor. So we are going to reuse this 5G signals to get this sensing information. So here are the parameters, then maybe later you can go in more detail. The SRS periodicity is 40 milliseconds. Okay, with this now I will give the floor to OBSmart team and Tiago. I don't know if you are ready to show the demo. The floor is yours.
Hello. Hopefully you can hear me well. Welcome to OBSmart and welcome to the live demo portion of this webinar. So today I'm going to show you a live demo here in our headquarters of counting people passing through this corridor with just 5G signals. So the test bed that we are using for this webinar includes an OAI AI running the OAI core network and G-Node B near real-time RIC as well. And this PC includes a powerful NVIDIA GPU card that you can use for AI and ML training and inference. So connected to this OAI box, we have the LiDAR radio unit connected via split 7.2, so full Open RAN architecture. And then connected to the network, we have this Quectel module acting as an ISAC illuminator. So this UE is sending SRS signals towards the G-Node B at each 40 milliseconds. Coming into this room, we have an iPhone 17 Pro, which you can see that is connected to our test network and is playing videos from YouTube in real time with a stable connection. We can control this entire test bed using our OAI box dashboard, in which you can see the two UEs, the Quectel and the iPhone, and you can see that the entire network is now running. So core network, near real-time RIC, and GNodeB, everything is up and going. So now I'm going to switch views onto our ISAC portion of the dashboard. And here I'm going to show you the amplitude and phase of the SRS channel estimate. And on these waterfall charts, you can see the baseline signature of the empty corridor. So now I'm going to ask 3 colleagues to go one by one, and let's see if we can count them. So João, please go in. So now João is going to cross the hallway, and here we can see his effect on the channel. Tiago, please go in. Now Tiago is about to cross the link, and here we can see the impact. And Guilherme, please, you are the final one. And here we could see the impact. So if I now move to the iPhone, I can now show the impact of just this gesture around the iPhone, and we can see the changes here on the waterfall chart in real time. So then you as researchers can leverage upon this data that you can extract from our solution with OpenAirInterface, and then train your own AI and machine learning algorithms and do your own use cases. This is just a simple showcase of what can be done with existing 5G signals. And now I'm going to pass on to Luis Pereira to show you how to go into the code and extract these signals. Thank you.
Thank you, Tiago. Thank you. I will share my screen. Hope I can see. I can share it. So can you see my screen, right? Oh no, it's in pink mode. Okay, sorry, I need to do one thing. Okay, so I need to drop and I will join from the browser. Sorry. Okay, let me try to share again my screen. Okay, can you see my screen now?
Now we see a black window.
Black window.
I mean, for me, this is all black.
Not yet. Can you see my screen? Camille, can you confirm?
Yes, we see the screen.
Okay, great. So now I will do a quick demo how you can do this with another tool instead of XApps and select rig. So we can do it, for example, with the T-Tracer, that is a debug tool provided in OAI that you can use, for example, to see the channel estimation. Okay. So starting, sorry, now you will see all the notifications anyway. So if you go to the GitHub of OpenAirInterface, you can see the documentation for the T-Tracer in the common folder, utils, T, doc. So here you have all the documentation, how to use, how to compile, how to record, replay, how to export, for example, messages to Wireshark, RRC messages and MAC segments and RLC and PDCP to Wireshark. And you can also have this kind of graphical interface where you can see a lot of things, so you can check the documentation later. And you can also create your own traces. So if you want a specific feature that is not yet implemented, you can implement it because it's open source. For example, in this example, we provide the LDPC decoding success, so you can check it. So from my presentation or my demo assumes that you are following this tutorial here for the core network. Okay, so if you follow this tutorial, iPhones will connect straight away to OAI. So I assume if you want to replicate, you need to follow this tutorial. One thing that I am missing is if you want to see the phase of the SRS, you need to use a branch that is not yet in develop. Paulo presented it in the PowerPoint, but I will show it here in the public repository, is this SRS T-Tracer. This branch only adds the phase of the uplink channel. Okay, so we start by starting the core network. So just the Docker compose up. Okay. So to use the T-Tracer, I will copy paste to be faster. You need to build some specific dependencies. So my suggestion is for you to build this way with this minus install additional packages. So it should be fast. So it will just install the additional dependencies required for the T-Tracer. And as you could see, it was very fast. Now you just need to build the GNODB as usual. Okay, I will use a USRP for this demo and Ninja, GNODB, and that's it. It should be fast. Now, in the meantime, while this compiles, so to run the GNODB, I will run this configuration file, okay, Vox.yaml, doesn't matter, and you just need this additional parameter, minus t stdout2. So you can check the documentation again. The difference is between 0, 1, and 2 for the T-Tracer, and to have the console logs, you need to use 2. Okay. Okay, I will close this, and I will move this here, and I will press enter. Since I added this parameter minus t stdout2, it will try to connect to the T-Tracer first. So let's do it. Let's start it. So you need to start another window, and you need to run or to go to this folder where the T-tracer is located, and you can make it first. It just takes a few microseconds, and then in the documentation you can check how it works, but I will go straight to this instruction /g-b -d, and it will immediately opens this interface. We will only represent the magnitude and the phase. Okay, this is just the minor changes, and the g-b is already running. Okay, so not sure if you can see me, my camera as well. I have one iPhone on my hand, and I will just connect the iPhone, and immediately you can see the magnitude of the SRS channel and the phase between this iPhone and the g-b that is located 2 meters from me. Okay, and this is with OAI, so you can extract this to your own application or specific use case. For example, if I move the iPhone to one side, well, I will try to do it. You will see a peak moving to the right. I'm trying. Moving to the right and now to the left. Well, the peak is not very deep, but well, anyway. So if I just move the iPhone, the line will move, and you can now use these samples, these symbols, for example, to use machine learning algorithms to do your own research. How is it? Where is this exported? So if you go to the code, I am using CLion, but you can use Visual Studio Code, you can use Vim, Notepad, whatever. Anyway. So for example, in this 5 procedures g-b, here you have this macro or this function, for example, that exports the frequency domain of this array, the SRS frequencies. Okay, and this is exported to the T-tracer, but of course the user can export it to other places, can save it or record in a file, can send these samples through TCP socket, for example, whatever. Okay, so very easy to export, for example, the SRS channel from the OpenAirInterface. You can do the same for SSBs if you are on the UE side, the same for CSI reference signals. So very easy with OAI and with the different tools and debug tools that can be used. And here I just give you the example using the T-tracer. Okay. So a second way to check the SRS channel. Thank you.
Luis, thank you very much for this demo. So what Luis present is based on the current implementation of OAI, how it's possible to extract the uplink SRS signals that you have demonstrated using our OAI box dashboard, but it's also possible for the OAI community to explore this data using the T-tracer to train your models. And maybe Camille, can you help me with the questions that are open? Maybe we can briefly go through any urgent questions
Yes,
before
sure.
conclude.
Yes, so we have some questions in the chat. Let me take some. There's one question, which is, can we use other reference signals for ISAC, for example, DMRS?
Using the DMRS, Luis.
Yeah, so as I just mentioned, if you use the OAI UE, for example, you can use SSBs that are broadcasted, so the UE doesn't need to know any configuration from the cell. Of course, if you want to use the MRSs, then the UE needs to be connected, but it can be used, yes, both for the DLSCH or the ULSCH, depending if you are using the signal on the UE side or on the g-b side. So both can be used, it's just a matter of the use case.
Okay,
Maybe I
thank
can
you.
add to this. So the DMRS is quite good. It has good autocorrelation characteristics, But one of the main issues that needs to be taken into consideration that DMRS is always comes with communication. So how can you separate it from communication and make it only for sensing? So that would be one of the challenges.
Yeah, that is a huge challenge, yes, because if the GNOD is just scheduling 5 PRBs or 10 PRBs every second to the UE, then you cannot do sensing because the amount of data is very low. Yes, thanks, Ibrahim.
Yes, thank you, Ibrahim, as well. There is another question, which is, do you have ISAC except code available at GitHub?
So what is available right now is a way to export, for example, the SRS that I just showed. So you can use tracer to record the samples or the channel, and then you can use it. But so far, at least, no, there is no public repository with XAMPP for ISAC.
Okay, another question is, where can you find the OAI box dashboard that was shown at the start of the demo, which had additional tabs for digital twin and ISAC CSI data real-time visualization? As far as I'm aware, this isn't the standard OAI box dashboard.
I can
So
take that question.
Yeah.
Yes.
This is a particular version of the dashboard that we are going to launch soon. It's part of our roadmap, and it has a localized approach. It's not running just on the cloud. It leverages your local area network as well as some inputs from the cloud to then show you more signals. So this is a question that we can answer on our backend, on our channel.
And
through
Tiago,
support.
why do you need to have a local approach for these kind of ISAC studies?
Because it would not be scalable to have every OAI box sending these types of signals which consume huge bandwidth towards our server and then back to the customers. It would just not make sense. So that's why this is a version of the dashboard that will run on your OAI box. Just reach out to us via the support portal. We will be happy to help you there.
Thank you, Tiago. I see that Kevin raised a hand, so go ahead if you want to speak.
Yeah, can you hear me?
Yes.
Okay, thanks for the presentation. I just want to know that if you want to basically localize an object, what was the precision that you got from your tests? And the point is that when you want to estimate basically the position of an object using, for example, SRS, the thing is that this timing that you are estimating from channel impulse response, it's not stable. It basically we have a synchronization issue between the clock of the UE and the GNOD, plus the time that we are estimating and extracting, it varies a lot. So it's not like a fixed time, a fixed index that you can extract it from channel impulse response. It varies a lot by the time, and basically you cannot get the certain number for estimating the position of a target. So I want to know how you deal with these issues. Plus the clock also have a drift. So we have some, this makes the accuracy of the positioning a bit challenging. So it degraded the accuracy. So how do you deal with it?
Okay, thank you for the question. So if you look to the slides, there is a formula for the resolution that in case you use 100 megahertz, the maximum is 1.5 meters. Although our objective here is to design a tool, a test bed for others to test AI ML algorithms. So today the objective of the demo was just to detect the presence of a person in a specific area. We are not going to test how accurate is the position tracking. So it's something that we didn't test. How we see our role as enablers for others to do research based on the data that we can expose to the OAI stack. But if you see in the literature, there is already several papers that use OAI and SRS. I can forward to you some papers with more accurate data.
So maybe I can add also a few words. So the main goal for us and for OAI is not to localize objects, is just to show and provide a tool like OAI that helps research to do that. Okay, it's not our goal, but
Okay, so
with
you have not to
OAI,
look.
with OAI, OAI provides the tools and interfaces and the code for researchers to do it and implement new possible 3GPP features in the future.
Okay, so you didn't do positioning actually yourself yet.
No, we didn't do a position. No, we are just testing in this use case that there is, for instance, a detection of a person in a specific area. We didn't train a model for localization, if you mean. But what we provide here, as Luis mentioned, is the enabling tools as a testbed providers for researchers to do this localization.
Okay, because actually I'm working on it currently, and it's a bit challenging. There are many things. So the time that I'm estimating from this, we have FR2 test beds that we are testing here. So the time that I'm estimating, it basically has a very big variance. It makes it challenging, and it's also asynchronous clock between the UE and also the G node B for when we are using SRS. It's a lot. So I was wondering if you have any insight on that.
Well, I don't know what you mean by it's a lot.
So meaning that, for example, when you're extracting the intakes of the maximum amplitude, it varies, for example, between, the index, for example, 10 to 40, 60. It's a number of the index. It's not a fixed number. It's not like so because you are monitoring on real time. So that's what I mean for, when it has a variance.
Okay, my advice for you is to join the OAI developer meetings on Thursdays, and maybe you can raise that question there, and you may get support from better support from the developers and community as well, or you can use the mailing lists because it's not so easy to answer without any data.
Okay, thanks.
Yes, thank you, Luis. And Kevin, I just shared the link for the developers meeting in the chat. In matters of time, I think we can take Nada's question, and then maybe, Paulo, you can share again the contact information you shared at the beginning of the webinar. So if more people have questions, they can just use the contacts you shared earlier.
Yeah, so I will have here my email, and we'll be happy to take questions offline. I saw a question regarding using the OAI UE. Just to tell you that it's possible to use the SSPs and the CSI. We have tested it, okay, but we have selected SRS today for the demo. But yes, to OAI UE is stable enough for extracting the SSPs and the CSIs to do the downlink channel estimation, and then from them to do ISAC research. You can just also Google OAI box, go to the forum. You can contact us if you several ways to reach us. Okay.
I don't know if you can. Yeah, okay. So thanks for the presentations and for the live demo. I have a quick question about the RIC and the service model. So I saw that you used FlexRIC, and about the E2SM SRS, did you implement a new implementation of that service model, or did you use the existing one?
Yes, okay. For the Luis, just for the sake of time, the demo that Luis presented didn't use the XApp, but it's possible to and I think there is a branch in OAI that implements E2 service model for SRES.
Yeah, it is a starting point, and it's exactly from her.
Yeah,
Yes.
okay. So that's some work that Florian team has done, and yes, if you want to follow the ORAN architecture, you should be able to use XApp and to expose this data using the E2 interface. So OAI allows you to do this.
Yeah, thank you. I just wanted to know if you use the new custom implementation or use the other one. Thanks a lot.
Okay, maybe last question from Madhu Sudan. Sorry if I mispronounced it.
No, that's fine. Yeah, you did quite a good job. So this is for the interdigital person. In the monostatic sensing case, you mentioned three, if you go to the slide, 3 reference points or 3 points, what, if you can put up the slides quickly, I don't know if you have the time. The interdigital person who presented.
Ibrahim slides?
Yeah, that's right, yeah.
Okay.
Yes, you're muted, Ibrahim, if you try to speak.
Can you share the
Oh, yes,
presentation?
sorry. Yeah, yeah, I can share the slides, just a moment.
I think a little bit further down when you're talking about the monostatic sensing case, you mentioned
This one here.
This is not the one further down.
So this one was on monostatic.
This is there was one
like one on the channel modeling. The other one
channel
was
modeling.
This is monostatic, and the 6G. 6G, like yeah, it will
Hold
be
on a
beyond
minute.
monostatic. Maybe this one.
You mentioned 3 anchors or 3. No, I think I'm missing that. I forgot to write it down when.
I think slide number 3.
Was.
Slide
number 3.
This one is on ITU.
No, this is not the one. This is not the one.
Yeah, probably it's so we have the channel model here.
Yeah,
and then the
monostatic sensing uses 3 reference points. Maybe it's that. Actually, it wasn't quite that. Maybe it was the same 3 reference points. That was the one before that we were just showing. Maybe it was that. I think it wasn't that. So when you're doing monostatic sensing, you have some kind of anchors. Is that what you're talking about? Because with monostatic, you have the let's say the G node B, and that's it. So what are the 3 reference points that are being mentioned here?
Yeah, so for monostatic, we have 2 types of monostatic. So it's either TRP based, which is like the G node B doing the transmission and the reception, and you have the UE monostatic. So in this case, it's not this one. This one, they focus on the G node B monostatic, but typically what you do is like you're transmitting some downlink reference signals. I wouldn't call them downlink because in this case there's no downlink. It's just transmission and listening. Yeah. So for example, if you transmit CSI, DMRS, PRS, different types of downlink SSBs as well, reference signals, you have to wait for some time, like you have the listening time, and then based on some prior knowledge about the environment, you can detect as done by the demo now. Like, I mean, always you have the reference measurement, which is the idle state, if we can say, and then whenever there's a change, you detect those changes. But I'm not sure I mentioned any like 3 references.
In your slide, monostatic uses 3 reference points. The modeling approach, the bottom of that. Last line. Very last line. No, on the left-hand side, the box on the left-hand side.
Oh yeah, so this actually looks at the channel itself, not as reference points. That's like when you have like the background, you have the so the reference points here would be, so first of all you have the communication channel, which is known to you through CSI, and then you have the positioning information of the G node B, That's the main ones.
Okay, I'll take this offline because I was wondering if you're referring to anchors in the environment. Looks like you're not referring to anchors in the environment. Okay.
Yeah.
Okay, thanks.
Yeah, cheers.
Thank you, Ibrahim. So I think because we are a bit over time, I think we can stop here. And we can stop here. And if you still have questions, you can still reach out to All Be Smart team. And also, if you want to join the OAI developers meeting, there's the link in the chat. And I want to thank our colleagues, All Be Smart, Paolo, Luis, Thiago, and also Ibrahim for this really good Experimentation Digital for this really good webinar. And thank you everyone for joining.
Thank you.
Yeah, thank you.
Bye. Bye.
Thank
Yeah,
you.
great. Good job, guys. Thanks. Yeah.
Thank you.
Thank you so much. Thank you.